All right. Oh, that was loud. Okay, can you hear me? Yeah. Wake up. All right, welcome to this session of Environment and EOR Solutions. And uh, Paulo Coelho from the University of Rio and also the COPE is my co-chair. I'm Steinar Sanni from Iris, no, Norse. I have to learn the new name after the merger. I used to be in Iris, I'm in Norse now, and also the University of Stavanger. And I have been organizing this for a couple of times now with my colleague Ying Guo, who is also in Norse. And we have tried to merge these two topics of EOR and environment because somehow they fit together. And we've also hoped that we could get some presentations that dealt with the environmental aspects of EOR. So we'll see. That we know that this is something we had to be a bit patient about to achieve because it's something that needs to mature. But there seems to be movements on that in both countries now. So we might address, yeah, come to that. So our topics today is, first of all, to get into talks some overview of the EOR issues that are of special interest in Brazil and Norway. So we can see common grounds, if there are any. And then we will present some of the more specific EOR solutions that we are working with in Norway. And then we will also have some topics presented more in the kind of the margins of EOR from some Brazilian partners. So that's our, yeah. Do you have anything to add about that?
No, I think I will start the presentation.
Yeah, because he's the first speaker. So just a few practical things for the speakers where you can introduce yourself, as it has been in the other ones here. Paolo and I will try to stay invisible, but we are going to try to stick to the schedule because it's quite tight. So then I leave the floor to Paolo for the first talk.
Thank you very much, Steinar. It's a pleasure to be here in the November conference again. I hope that by the end of this conference we can strengthen the collaboration talks we are having with the Norwegian institutions and the Brazilian universities as well. So, as Steiner has mentioned, it's very nice that we can merge environmental and EOR techniques together because nowadays these two disciplines cannot walk and separate anymore. They are very they're strongly related to each other, and I'm gonna present you some data today that will reinforce this idea. So basically, I will talk a little bit, very shortly, about multi-scale core analysis at the laboratory we're running and how this analysis can represent a solution for offshore Brazilian fields in terms of enhanced oil recovery. I'm a professor of the petroleum engineering course at the Federal University of Rio de Janeiro for 12 years, and I've been doing research on oil and gas area for about 16 years here in Rio de Janeiro. So I would like to start this presentation with news that were presented at the newspaper in August 2017. It's in Portuguese, but I translated into English the most important part. It relates to Mero 1. It's the first well of Mero field, one of the major fields in the pre-salt. The project will consider 18 producers and 9 water alternating gas injectors. It means that Mero field will start with EOR from the beginning. Okay, so it's the first time an EOR project will begin here in Brazil, specifically the pre-salt area. Okay, so it's connected to an FPSO with a producing capacity of 180,000 barrels of oil a day. So this is a challenge for the industry. Why this is a challenge? Because here we have the production of the post-salt fields in Brazil. We can see clearly that the campus basing start the declining curve now. All the Brazilian post-salt fields are entering into the decline period now. Okay, this is Campos, Santos Basin, and Espírito Santo, and this is the northeast basins offshore. This is offshore production. Okay. On the other hand, we have a new frontier, the pre-salt frontier here in Brazil. We can see here the pre-salt production increasing every year. And by the end of 2017, we were producing more than 50% from the pre-salt than from the post-salt. Okay? This is the total production per year, and this is the post-salt and the pre-salt. So, on the other hand, I took this data from OPEC showing that oil demand will still increase along the years. It means we'll still need more oil in the forthcoming years. So we have to keep this in mind when we are producing in Brazil. Okay? This is because here in Brazil, not much EOR has been done in our fields. There's a lot of infield drilling, but not much EOR projects, specifically in the offshore area. In Brazil, 95% of our production is offshore. And we are not applying too much EOR on these fields. And they are declining now, okay? So this is because we have poor models for EOR. This is the major problem for these techniques. We have plenty of models for primary and secondary recovery because we have a lot of historical data to do history matching. But we don't have history matching for EOR. So this is a major problem. This is because EOR involves complex physical and chemical interaction, okay? Therefore, the models for EOR, they have to account for these interactions, and they have to present a good, reasonable prediction to be used. So this is one of the bottlenecks, the lack of reliable models for EOR. Okay. This is some data from the pre-salt. Okay. I took this data from the last report from the Brazilian Petroleum Agency. It's the first well producing in Mero. 42,000 barrels of oil a day. If you consider gas production, it goes up to 60,000 barrels of oil equivalent per day. It's a huge production. It means we have a high production reservoirs. We have a high quality but very complex reservoir. They are very heterogeneous, can go to water wet to oil wet in a matter of meters. So they are very complex structures. And they are very large structures. For example, Libra field was the first field in the pre-salt that was bidded. The estimate, the oil recovery estimate goes from 8 to 14 billion barrels. Okay, recoverable. So they are very large structure with light oil. So the average daily production in the pre-salt in September, last September, was 1.78 million barrels of oil equivalent per day. It represents 55% of total Brazilian production. Okay, so, and behind the pre-salt, we still have a lot of areas to explore. Only 6% of the sedimentary basins in Brazil were already explored. It doesn't mean we have oil in the other 94. We just don't know what's going on the other 94. So there's plenty of area to explore. That's why I say EOR time in Brazil is now. It was not 30 years down the line when there was plenty of oil and cheap oil. And it's not 30 years from now, because 30 years from now, someone will come up with a new technology. So EOR time is right now in Brazil. Okay. Here's another example of that. So the average oil recovery in Brazil is only 21%. only 21%, and our offshore post-salt fields are in decline curve now. This is unacceptable. We are doing a very bad homework. We're doing a very bad job in terms of recovery. We can do pretty much better. If we consider campus basin, this number is a little bit better. It's 24%. But compared to the world average is 35%. You know regions, you know that you have you have examples up to 70% in Norway. You know, if we increase in 1%, that 21%, if we increase in 1%, we add $11 billion in royalties in the oil and gas sector. We add 2.2 billion barrels of oil equivalent in reserves. We add $18 billion in new investments in the market. So it's not, it is a big deal to invest in EOR. The reward is very huge. It can be very huge. For example, Libra. If I increase in 1%, the worst estimate, we increase in $5.3 billion the gross income of the consortium. $5.3 billion. So this is a huge reward to invest in EOR. And that's what we are doing at the university. We are developing this laboratory for some time. Okay, we are focusing on the carbonate rocks of the pre-salt. Okay, doing experiments in reservoir condition to recover more oil and to help understand all the interactions between rocks and fluids in the pre-salt. And how are we doing this? Well, first, this is where we are, Rio de Janeiro. I'm going very fast on this. We are right here, right now. That's where we are right now. And the laboratory is close to the international airport in the campus area in this region here. So this is the Center of Technology of Federal University of Rio de Janeiro. We are very close to the technology park of the university and very close to the research center of Petrobras. So I used to say that we are in a very special and strategic location because we are very close to the research center of Petrobras and very close to the main oil producers in Brazil. Okay, these are some pictures of the laboratory. I'm going to run very quickly through this. And this is the idea of the structure of the labs we have in our university. The Enhanced Oil Recovery Lab is just one lab in the frame of the interdisciplinary group of fluid dynamics. We have well technology, we have multi-phase flow, we have compact separators, we have turbulence lab, instrumentation lab, and microelectromechanical systems lab. With all these groups of lab, we can do research from the reservoir to the separator in the surface, passing through other disciplines related to oil production. Okay? And how we are doing this multi-scale? We have now, we are doing research on wettability of rocks under reservoir condition. I'm going to show you some pictures later. In the pore scale level, using micromodels to observe the displacement of the fluids. We're doing digital rock physics as well, using this data to validate this model. And we are doing also some core floods to understand how the displacements occur in reservoir condition. So the idea is to take this whole set of a scale here and try to take this information to the field scale. Okay, so this is where we start. This is the results of a master thesis that was presented a few months ago, where the student, Fernanda, she studied these coquina samples. These coquina samples are taken from the northeast, from a quarry in the northeast, in Sergipe, Alagoas basin. They are very similar to the rocks of Libra field. They are the same age, porosity and permeability are very similar, and composition of the rock is similar as well. So this is a good material to work with because we don't have much access to real rocks from the pre-salt. So she characterized this. These data are then used in another scale where we do wettability analysis. The results of these wettability analysis will be presented now in December by Santiago. He's going to present his PhD thesis, and he's done a very interesting analysis on how CO2 concentration affects wettability of the rocks on the pre-salt. Okay, these are very interesting data. Here's some initial data here, and these results were made under reservoir condition. I mean, high pressure, high temperature, okay, with real oil from the pre-salt, dead oil, but recombined with CO2, formation water, and real simple rocks. After that, we are also modeling all this fluid flow through micro CT scans of the rock and pore network models. We are modeling how the fluids flow through the rock, trying to recover the rock properties. We are also comparing, this is one of the pore network model that was developed. We are, William is doing this in his PhD thesis. Now he's connecting macroporosity with a microporosity region here, okay? This is one of the huge problems of the pre-salt modeling, I mean. And, okay. We are also comparing this with core flood experiments we are doing at the lab. I'm going very quickly through this. These are some initial results where we got some increase in oil recovery by using carbonated water instead of injection water. So we are comparing this data with the modeling and using this data to recover also relative permeability curves for the carbonate. This is one of the experiments using Indiana limestone where we got a wormhole here after the injection of carbonated water. This is very interesting. Okay. And this is what we got right now. It's a large core flood rig equipped with an X-ray scanner. This will allow us to do saturation tracking in the rock under reservoir condition. I mean, 10,000 psi at 150 degrees Celsius. This equipment is already in the lab, is not installed. We're just waiting for the engineers to come and plug it so that we can start all the analysis with that. Okay, another view of that. So some view of the lab. I'm going very quick through this because I'm running out of time. Okay. And we are now involved with several other projects in terms of EOR at the university. These projects are mainly funded by Shell. So we are running the WAG project in our lab to study water alternating gas using CO2 as a recovery fluid because, as you may know, CO2, the production of CO2 is one of the huge problems in the pre-salt. In Lula field, 40% of the gas production is CO2. This 40% represents 600,000 cubic meters a day. You cannot just throw it in the atmosphere. So what they are doing in Lula field, they have 2 injection wells, and they are using these 2 injection wells in a WAG process. While one well is injecting gas, the other one is injecting water, and from time to time they change. So WAG is one of the techniques that's been seriously considered for the pre-salt production. And Petrobras has already experienced an increase in the recovery factor in the area they are testing this in Lula field. Okay. We are also involved with the polymer flooding project developed at the Macromolecules Institute. This is very interesting because they are developing a biopolymer to be used in the pre-salt. So a biopolymer is more environmental friendly, is not so aggressive. And we are also studying the use of, we are collaborating with the Catholic University of Rio de Janeiro, where they are studying the use of surfactants and CO2 foam for EOR. So the idea is to reinject the CO2 in a kind of CO2 storage process, okay? Because CO2 is the best fluid you can inject at the reservoir for EOR processes. Okay, I'm about to finish now, so I'm going to run through this. This is the team involved in the WAGX project. Okay, we have several researchers and several PhD, masters, and undergrad students all working together. This is the team for the other project we're running. It's basically a PVT project, so we have a very large team, but it's important to say that we are supporting several PhD, masters, and undergrad students with these two projects here. And this is the collaborative network we are setting up now. We have a very good collaboration established with Heriot University in Edinburgh. We are now celebrating a collaboration with Utrecht University in Netherlands. We are discussing very seriously with Ghent University in Belgium, the collaboration, and start discussions with Imperial College. We have collaboration with the Catholic University in Brazil and Unicamp in Sao Paulo. And we are planning to extend this, and probably and hopefully with Norwegian's Institute and with the support of Norwegian's oil companies, of course. Okay, so that's it. The pre-salt is here. It represents a challenge. Okay, most of these challenges are related to environmental issue, as the CO2, the high CO2 production. There are fields that are producing over 40%. Okay, so this is a huge issue. Also, production of water is an issue because of the salinity of water. It's a high salinity water. It's 225,000 ppm of salinity. So it's very aggressive. You cannot just throw it in the ocean. That's why I say that environmental issues are not separated anymore to EOR activities. Okay. Well, thank you very much. This is a picture of the team. Thank you very much. And during the sum up, I'll be glad to answer all your questions. Thank you so much. Thank you, Sarah.
Okay. Thank you,
Sorry for passing a little bit the time.
It's fine. That was mighty fine. A lot of information in a very short time. Very interesting. And okay, shall we wait for the questions?
At the end.
At the end. Okay, that's good. Now we'll have my colleague from Norse, Jan Ludvig Vinningland, who will give an overview over the Norwegian IOR Center of Norway.
So, hello everybody. So my name is Jan Ludvig Vinningland, and I am a senior researcher at Norse, and also one of the team leaders of the IOR Center. So let's see, I need to keep track of time, so we're a little bit past 5:02, so yeah. It's noted. Okay. There's a movie now. Let me see if I can show this movie. It's a movie from the conference we had in April this year. Is it? I don't know how I start it. If I do like this. No, that was the wrong button.
I'll do that for you.
Just now you can click start. Yes, enjoy.
I love being part of the center.
IOR Norway blitt en helt unik møteplass for forskere som driver med økt oljeutvinning, både fra inn- og utland. Så det idémyldring, mingling og bygging av nye nettverk.
Veldig positivt med så mye mulighet for å utvide nettverket.
And what better day to announce that the National IOR Center are getting continued funding from the Research Council of Norway.
This is the three partners that collaborate in this center: IFE, UIS, and Norse. And it's hosted by UIS. And you saw Merete Madland, who is the director of the center there in the end. And we are located this is we are located in Stavanger, of course. This is the used to be the headquarters of IRIS, and we are in Bergen, and we have collaborations in Trondheim with the Ugelstad lab, and we have also people sitting in Oslo, and the IFE headquarters is also there. And there's another center, a twin sister center of the IOR Center, doing research on Arctic exploration in Tromsø. So what we want to do is to contribute to improve recovery on the Norwegian continental shelf, and do that through research and development to have field implementations, to take it from the pore scale to the core scale up to the field scale, very similar to what you, Paolo, were explaining. And the vision is to join forces to recover more. So this is our partners. It was established in 2013. It's already quite a while ago. It was recently midway evaluated, and you saw from the movie that it was granted for the 3 remaining years. So there's a green light for the 3 next years, the 3 final years. We have a lot of very strong collaboration with industry. So we have 11 user partners from the industry. And this is very important for the center. And of course, Norwegian's Research Council, the Norwegian Petroleum Directorate, and Petoro are observers of the center. And the budget is about 50 million Norwegian crowns. Yeah. And just a little bit, I mean, I won't go through, but maybe if some of you know some of these guys. So we have leading the technical committee is people from the industry. Nils Lindelof from now Total, used to be Maersk, and Thierry Loctre from Aker BP is chairman of the board. So it's a very integrated with industry. And we have the split in 2 different themes. So one theme 1 is focus on immobile oil and enhanced oil recovery. And then the team 2 is more focused on mobile oil, how you get better characterization of the reservoir, how you get better microscopic sweep of the reservoir. I'll come back to that. And we also have a scientific advisory committee that we have meetings with once a year, and that we discuss important decisions with. So, and these are really high-ranking scientists. So it's a very good foundation for the IOR Center. And the technical potential for enhanced oil recovery on the Norwegian continental shelf. You see here, this is in green. This is the remaining resources after planned field and under current improved plans. And this is, let me see, this is the remaining oil reserves in this green here. And in addition to that, they estimate that 7% can be extracted in addition using IOR methods on the Norwegian continental shelf. Almost the same amount as what is remaining reserves. So it's a huge potential on the Norwegian continental shelf. And this is, I think, based on the 27 largest fields on the Norwegian shelf. So just a little bit about the IOR methods that we are focusing on in the center. So you have microscopic sweep is then to get more displacement, or get the oil out that is behind behind the oil front in the water area. And then macroscopic sweep is to get better diversion, or to get oil in a larger scale to move more like a piston. So this is, of course, this is the advantage of polymer flooding. You get a more stable displacement of the oil, and you don't get this fingering behavior as is common with water. So polymer is important for the IOR Center. In addition to that, we also look at how you can optimize the water that you inject in the reservoir. You can use low salinity flooding, or you can also have what we call smart water, so that you inject or remove certain chemicals to get a better displacement or get increased recovery, or you add some chemicals. But let me note that this is chemicals that's already in the water. We have seen, for example, that sulfate is very important to have higher recovery. So it's just a kind of tuning the chemicals that is already present in the seawater. And polymer is also we use green polymers. And then you can also use silicate to have water diverging techniques. I mean, to push the water into new unflooded areas of the reservoir. And the silicate will turn into a glassy phase in the reservoir and kind of plug the most flooded regions. And it was just evaluated quite recently, and Anne Muggeridge, actually, who's one of the, in our scientific advisory board, was part of that, and they concluded that actually low sal and polymer is the best option for Norwegian continental shelf. And this was then, so we were quite happy with the choice that we made in the IOR Center, and that choice was based on close discussions with the industry. So it was not something we just guessed. So we came to the same conclusion, probably because we also talked to the same people as they did. And then it's the same thing. We want to go from the pore to the core scale. This is a triaxial cell where you can have high pressures and you can have injection fluids to see how the core behaves under realistic conditions. Then we go to the backyard scale, as we call it. So this is just something that was set up in the backyard of the IRIS facility to test the injection of polymers. And then we want to go to the full field scale. So the objective is to contribute to have a field pilot. But that is something that the industry needs to decide on. So we will just somehow generate enough information for them to help them to have a field pilot. Yes. So this is the 7 tasks that we have in the center. So this is more on you do an experiment in the core scale lab, and you need to see what happens to the what happens to the core. What minerals are taken out, what minerals are precipitated, what happens to the porosity. And then we have the nano submicron scale task, where you take images of the core, you slice it up afterwards, and Udo Zimmermann, who is heading this at the university in Stavanger, has a huge network. So he travels all around the world to get very accurate measurements of replacement. Here you can actually see the replacement of between magnesite and calcite. So there's a replacement process going on, taking out calcite and adding magnesite. So this is the pore scale process where you try to have simulations. We don't use pore network models as Paolo, but we use lattice Boltzmann methods. And we also use, this is a DPD, it's a kind of a molecular dynamic simulation of polymers. So we have a tracer technology in collaboration with IFE. So we try to get better knowledge about the flooding properties of the reservoir using green tracers. And we have reservoir simulation tools. This is the OPM, Open Porous Media Simulator. It's an open source reservoir simulator. And we have also a geochemical reservoir model, which is an add-on to Eclipse. You can use it as an add-on to Eclipse to add geochemical functionality to Eclipse simulations. And we have this field scale evaluation and history matching task mainly in Bergen, where they use ensemble-based methods to estimate to put in all knowledge of, for example, 4D seismic data, put in all the data and all the uncertainties, and try to evaluate all the different models to get a better idea about the total uncertainty in the predictions. Let me just skip. I don't have time for these. And we have a huge, we have a lot of international collaborations. Yeah, I will not go through that list. we are educating a lot of students, 29 PhDs and 19 postdocs so far, and we have around 50 master students each year. In having yes, and then I want to say something about this IOR Norway conference that you saw in the beginning. So we've had, this is the 5th so far. We will arrange the 5th now in April, or in March actually. The date, yes, in March. So I will encourage all of you to come there. Paulo, William, and Santiago, they were there in this year at least. And that's when we also started our first discussions about this collaboration with Paulo. So it's a good area, a good arena for having new ideas. And summary. So we want to increase macroscopic and microscopic sweep using green chemicals, such as polymer, and modifying the chemical composition of the injection water. And we also develop numerical models, both on the pore scale and on the field scale, so that the companies can make more precise decisions. And this test of polymer injection would not have been possible without the IOR Center. And I would say that this was Halliburton who was leading this project, where we test how polymers are degraded in valves when you inject it into a reservoir. Because if you lose the viscosity in the valves, it's no point injecting the polymers. So we learned that you had to use many valves and take down the pressure over long distances. And SNF, this French chemical company, they contributed, they worked free, voluntarily or without pay in this project. So it was a huge success that you really demonstrated what you can manage if you work closely with industry. And also the education of the researchers. Okay, that's over time probably.
Yeah, thank you. That was 15 minutes sharp. So, does anybody have a quick question, or we can also? Yes. Okay.
Quick questions. When you say green polymers, are you mean biopolymers or synthetic polymers?
Yes. But there you have, of course, you have biopolymers, and we have actually been. We have had a close collaboration with Wintershall and BASF for this schistophilan. Yes, the schistophilan polymer, which is a very nice biopolymer. But there is one thing about that, is that they usually inject biocides prior to the polymer, because if you have too much bacteria, that could destroy. I'm not an environmental scientist, but so this is something. The polymer is not. That's a perfectly green, but it depends on what you need to do to have the polymer operate under the right conditions. So this is yeah.
Okay, thank you. We had Jan Ludvig mentioned a few key words. One of them was smart water, and the other was tracers. And that's the two topics we're following now. First, it's from my good colleague, Professor Torleif Bygstad, who's going to talk about smart water. And after that, it's Rolf from IFE that will talk about tracers. So, vær så god, Torleif.
Good afternoon, in 3 languages. Smart water has been introduced. It's from seawater, has been introduced. It should be on. Can you hear me? It is on. The green light is on. Can you hear me? Am I on? Get into my... It's on. Is it still not... Hører meg så godt, så kjekt. Da det ingen som tunghørte. Men igjen, smartvann, from seawater, by membranes. And it is for enhanced oil recovery. And these are the 4 authors. And here we have the 3 languages. Good afternoon. And we used to call it designer water, because we can design the water we want. But that was taken by somebody else, and we could not use that word. It's just like a suit. We could not use that suit. But this is the campus of Stavanger, and this is facing west all the way to Scotland and Iceland and America. Little further north than here. Normal seawater, not dirty seawater. We know that is most of the globe, 70%, and it's saline. It is like 34,500 milligrams per liter, not like 100,000. This is fixed when it's normal. And here we have the normal ions, and sodium and chloride are the two larger ones. That is not, they're not large, but they are most numerous in mass. The sulfate is important, calcium and magnesium. So those are also on the top 5. And you know that drilling is not the same as production. We are now talking about production, long after Bernd has been drilling. Very important to know that for some of us. So primary oil recovery was mentioned from Paulo, that not too good recovery in Brazil. First stage, hydrocarbon production, natural pressure. I probably should introduce myself a little more, Steinar, because I have been at the university for 42 years. I'm a dinosaur, and I'm born to become a hydrocarbon. So there's a purpose also for me. Enhanced oil recovery. I knew that would catch on. Anyhow, oil recovery methods, we have gone through the primary, which is the natural pressure. Then we can start having some floods. Oil recovery methods, and you do see where you put in the water, and you see that plug that was mentioned, or maybe not the plug, depending on what you use. But you can then get up to 35%, which is not so abnormal. Water injection or gas injection. Then we talk about the smartness. Why not become smart and get more? And there are many methods to become smart, but there's only one sustainable, and that is to do something with the seawater, not add any chemicals. That is definitely green. We have talked about surfactants, and we have talked about CO2 in previous talks here, that smart water is either divalent or also low sal. Low sal is also smart. Don't get me wrong on that. That is for sandstones. The other one is for the chalk. I realize chalk. And we can then get up to 80. Or maybe even more, depending how smart we are. So this is a summary of what I just said, 10%. Secondary, and depending on if it is chemical EOR or water-based EOR. And the research center in Norway, they are handling both. They wanted to do both, even though the smart water is the best, of course. It's also called a signer, depending on the oil company. And here's the summary again. Primary production, it goes up fast, then it goes down, just like we saw from Brazil. Or we can do water flooding and perhaps get up to 20, and then it goes down, and then we can do tertiary. But this is the important, this is the accumulation of going uphill, not downhill like you saw in Brazil. That is, of course, the clue, of course. Same infrastructure to handle the smart water, so no expenses, just more oil. Oh, nice. Like an adventure, that is true. The big word is wettability. That was introduced also yesterday at the plenary session, wettability. Not just water wettability, but oil wettability, depending on. Wet is also oil wet. And that is the whole thing, how it sticks to the surface of the rocks in the reservoir. Oil, ore, and water. Wettability. And here we do see manipulation of ions. I don't like to be manipulated, but that's what we do when we make smart water from seawater. We manipulate, take out some ions, leave some ions. And here is what happens. Push it out. Leave the water, the smart water, but the oil is what we are paid for. So again, I repeat, this is the whole thing. Wettability is so important in this aspect. And here's the clue, how it works. Mechanisms for wettability alteration. And we had a good teacher, he's still around, but not much at the university, who said, if you can have sulfate remaining in the smart water, that is number 3 in the salt water of the ocean, number 3 iron. We don't need the sodium, we don't want the chloride, but we need the sulfate. Then that will neutralize this surface of chalk, and therefore we push down calcium and magnesium, the divalent cations, and they will release the oil. That's the whole trick. That is the mechanism. And instead of using all these things that we just mentioned as far as polymers, well, the smartness doesn't need that. And we get even more oil out from the same reservoir without any other things added than just sulfate from the original seawater. And here we do see some examples, again, experiments at the University of Stavanger in chalk or carbonate reservoirs. So here's just the formation water, which is in equilibrium over the last 200 million years in the reservoir, because we are disturbing the equilibrium by drilling and producing. We are disturbing something. So this is the formation water. We have the seawater. We get up to maybe 40%. And here we have seawater without any sodium chloride, which is low sal. But here we have seawater with hardly any sodium and chloride, but added the sulfate that comes from the seawater. And you do see magic. Magic moment. How we do it? By membranes. That was also mentioned in a previous lecture earlier this afternoon in another session. Sulfate. Equinor was talking about that. I'm a membrane man. We are all membranes, living examples, and we function. We are the best. We are membranes. The whole system here is membranes. The heart, the lungs, eye. So this is nothing new. Membranes has been around since the dinosaurs. Cross-flow membrane separation, meaning the feed goes in, out comes the permeate, and going through the retentate. And this is the sulfate. The permeate is sodium and chloride that we don't need, unless it is sandstone and low sal. We can use both. And here's the trick. Membrane is high-tech. This is the only high-tech part, how you make them. And the divalent will be returned. This monovalent will go through. At low pressures, meaning little energy. And we heard about today, if you had an application without mentioning energy, you would not be considered. This is low energy. We save energy by using membranes. And here's a thin film composite membrane. And it's a very thin layer. That is the only thing that's high-tech, how to make them. You need a good chemist. So, quality, efficiency, cost. And we call that membrane that we are using for nanofiltration. That means they are in a nanoscale as far as pore size, meaning sodium chloride will go through, sulfate are too big for the pores. They will be retained. Retentate. So, low total dissolved water, we can have fresh water and add chemicals, like Thor did in his experiments. But we can also use nanofiltration membranes directly on seawater, and the reject is the sulfate rich that we need for the smartness. So offshore, we don't have fresh water. Therefore, we have to make. Takes energy. Reverse osmosis is very high in energy, but it makes fresh water that we can add chemicals to, but it's not sustainable. We can obviously be onshore, but we are offshore, so bad luck, we are offshore. So therefore, nanofiltration and smart water, kilowatt hours per cubic meters, very low compared to all other alternatives when it comes to making smart water. So again, I repeat, nanomembranes, low pressure, RO membranes, high pressure, and they separate. This is a separation process. This is nothing new. In 1990, Marathon Oil had reservoirs that had lots of barium. And barium and sulfate, well, let me see, I thought I had another slide here. The barium and sulfate are lovers. They like each other so much that they actually clog the pipes. Therefore, sulfate was taken out of the seawater before injection into that Marathon field, and it has worked ever since, almost 30 years ago. So then again, nothing new. 30 years ago, I was part of that sulfate removal project for Equinor, by the way. Produced water is another challenge. It's not just how to get out more oil, but also what do we do with the produced water. And here we can see it dumped sometimes, but again, lots of produced water comes up with the oil. And that is what we could do something about, not just use the seawater offshore, but the produced water. And perhaps make that smart. Produced water management, and you do see how much is coming off all the time. It's a nuisance, it's a problem, it's a challenge, how to get rid of it. Well, let's make it smart. And that's what we have done in our lab, again, and also meeting some challenges. Because we heard about these 100,000 milligrams per liter of ions. Well, this is also very high in totally dissolved solids, produced water, and need good pre-treatment before the membranes. Make it smart, but it can be done. We did that, pre-treated, activated carbon anthracite. Looks beautiful after mixing with Ecofish oil, and this is how it is. Pre-treated, produced water, right into the membrane, becoming smart water, and used. So again, the conclusion, more or less, right, Steinar? More or less? Perfect. I like perfect. Chemical consumption, 0. That's why it's so green. It's sustainable. Cost is therefore low. Needs some energy, as I showed, 9 bar pressure. Sustainable and oil recovery. So again, here we go. Norske fregatt. Not grounded this time. Anyhow, smart water, nanofiltration is the name of that membrane, the pore size. And hello, Captain, and again, Robinson Crusoe, we use our technology and smartness and make things not necessarily with burning hydrocarbons. We can have a windmill. We can use the pressure, and we save this fellow who has been looking for water for a long time, Robinson. And here is the team. This lady, whose work I have presented now, delivered her PhD thesis yesterday. She'll defend it in February from this EOR center, financed by Skule, a professor. He was the Prince of Elsa, by the way. And here we have a nice lady from Murmansk. Nice teammates. And again, I learned a little Portuguese, or is it Brazilian? I don't know. Mange tak, thanks, and that's it.
Thank you, Torleif. Quick questions? I think it was perfectly clear, actually. So, thanks, Torleif. And then we move on to a contribution from our other partner, IFE, and Rolf Nyborg. And it also, his talk is about this single well chemical tracer tests. And it also has environmental aspects, a green shift for these chemicals, making it being considered in barrels down to vials, right?
Thank you. Okay, my name is Rolf Nyborg. I am actually head of the corrosion department at IFE, and you might wonder what the corrosion guy does here. But 2 years ago, I was also temporary head of the tracer department at IFE, so I know a little bit of tracers. But the real expert here is my colleague Christian, who is now heading the tracer department at IFE. Okay, just very short background here. The measure oil saturation in two different types of field operations. One is perhaps most best known, the partitioning interval tracer test, where you inject a tracer at an injector well, and then you see what comes out in the producer well somewhere else. The other is this single well chemical tracer test, where you inject a tracer in an operation in the single well and let it float out in the reservoir, and then see what is, how it is producing back. What is usually needed here in this single well chemical tracer test is that you inject a primary tracer, which is typically an ester, which is then reacting by hydrolysis when it meets the formation water. So you produce an alcohol and an acid typically. This means that you will have two different chemicals coming back here, and the time lag between these two chemicals will then give you a measure of the oil saturation in the near well area. Okay, so this is a picture of a typical offshore single well chemical tracer operation. It typically involves somewhere around 100 to 500 kilo of ethyl acetate, and also similar amounts of isopropanol and normal propanol. This means that you have quite large volumes, so you have large volumes which has to be transported offshore, and this is also highly flammable substances, so there are health and safety issues quite serious about this kind of operation. This is from an operation where IFE has been doing this offshore, and we have this small office here, and the actual work going on in this area here. Typically you need 1 day to inject this stuff, and then you have to shut in the well for 2 or 3 days and wait, and then you have the back production in two days, where you do the sampling of what is coming up here. So that is the traditional way. What we have been doing here is to see what can we do to improve this situation. One point is that it is a very large amount of chemicals which is required to do this, and also because it's so much chemicals you inject, you may actually you have actually the risk of altering the system which you are trying to study, and of course we don't want to do that. For instance, you can alter the pH value in the water because it's so much here. And with this traditional way, you can only use one tracer at a time. It requires a lot of space, and you have this health and safety thing. Okay. So what we then went out was to develop new tracers which could overcome some of these negative effects. If you can reduce the detection limit from, if you can reduce the detection limit from 5 ppm to 5 ppb, then the amount you need to inject is reduced from 500 kilo to 500 gram. So it is to a large extent a question of finding tracers which you can detect in extremely small concentrations when they are produced back. Okay, so we had a quite large joint industry project running over several years with a large number of oil companies as participants, where we tried to find new tracer candidates. We also, in parallel, developed more accurate analytical procedures to be able to detect this in much smaller, lower concentrations, and we had a simulation activity going on. I will not go into details about this, but I will focus on the last task, which was a field test, where we had an actual field test of some of the chemicals or the new tracers which were developed in this project. And we have been doing this for many years, so we have sort of an experience-based workflow where we first identify different candidates and then look on the availability. Is this something we can purchase, or do we have to synthesize this ourselves? And then we have to develop a chemical analysis which can measure these compounds in very small concentrations. Then it has to go to a qualification process and meet some acceptance criteria. And typically in this joint industry project, we were studying like something like 200 different candidates, which went through this loop, and most of them stopped here. They didn't meet the acceptance criteria, but we were able to identify a few compounds which were very promising. What we did then was that we were able to run a field test in Saudi Arabia in cooperation with Saudi Aramco, which was one of the participants in this project. And this has actually been published at the conference, and it will be an SPE paper. And I will not go into detail about these curves, but this shows a comparison in this field test between the traditional usual tracer, which you have to inject in large amount, and the 3 of the new developed tracers. And you see, the form of this curve indicates that the new tracers behave much like the old ones. The shift over here between some of them is just an effect that they have been injected at different times during the same operations. So what is injected first comes last back, or the other way around, or something like that. Anyway, this difference here reflects, that corresponds to the amount of produced oil in that period. So it matches very good. Okay. And the key here is that we have been able to identify chemicals which can be injected, not in very large amounts in several drums, but in small vials like this. So in fact, in this case, we were able to inject around 50 to 80 milliliter of these tracers and get the same good results as in the traditional tracers where you inject several hundred kilos. Another point here is that with this technique we are also able to inject different tracers at the same time, and what we have been doing here is to inject 3 different of these new tracers with different properties, so they will go to different parts of the structure, and we can also then, by measuring the time when these are produced back, get a better understanding on how the reservoir differs in different zones out from the well. So we get first of all a very good correspondence between the old method and the new tracers, and also we get additional information from it. So that is very, very, very promising. So the investigation depth depends on the K value. So, and this gives a saturation estimate which is specific for each zone in the reservoir here. So the story is, the short version of the story is that this is sort of a green shift reality, because we are able to reduce the volume of traces from several hundred kilos to a few milliliters. So it is much less chemicals which are used and which is then produced back, of course. This is a picture from this field test in Saudi Arabia. So there are other places which are also hot in the summer. And we are also doing continued research on this, where we are trying to optimize this technique to look more into the properties of these different new tracers and gaining more experience. And we are also looking into improving the detectability and the analytical methods to get this even further. And we are also looking into using nanoparticles where we can get more information out of this. So that was the short version. I am sure that Christian will be able to give a long version, but that's it. Thank you.
Okay, thanks, Rolf. So I registered that the two last talks are about no or less chemicals, which from an environmentalist side point of view, like myself, sounds brilliant. So does anyone have any questions for that? Magne, please.
Yeah, Magne Synes from university. So I'm wondering if you traces what kind of chemicals are there?
I don't have the details about that. There are some sort of halogenated chemicals which are synthesized in our lab. So there are compounds which are not found in the reservoir. So that is one of the things which make it easier to detect in very small concentrations. But I don't have the actual composition. You have to ask my colleagues about that.
Thank you, Rolf. Then we actually have a coffee break, and we thought it was good in the afternoon. Yeah, so we'll be back here at 5 after 4. So.
Por favor, Clécio de Bom se encontra na sala? Clécio de Bom?